Use your phones. If you think you have the right answer, raise your hand, come up to the mic, answer the question correctly, and there will be prizes. It's PE study guides. So when we get to that, I'll let you know how we're going to move forward. So with that being said, our first presentation today is on evaluating storage stability and performance characteristics of recycled composite plastic modified asphalt binders. It will be presented by Sheikh Muhammad Imdadul Islam, who is a PhD student in Civil and Environmental Engineering at Rowan. And he is also a graduate research fellow at the Center for Research and Education in Advanced Transportation Engineering Systems. Whenever you'd like to begin.
Good afternoon, everyone. I know it's very hard to hold the concentration after the lunch, but just hang on there. Just making sure, can everyone hear me clearly? Well, good afternoon, and welcome to my presentation on evaluating the storage stability and performance characteristics of recycled composite plastic modified asphalt binders for 27th Annual NJDOT Research Showcase. I would like to thank the whole CREATES team from Rowan University under the supervision of Dr. Yusuf Mehta, and also I'd like to thank the US Army Engineers Research and Development Center for funding this project. Before going deep into the presentation, I'd like to share a quick update on the project that I'm working on. That two of my papers, including the one I'm presenting now, they have been accepted for the presentation at TRB 2026 and also recommended for TRR review. So the whole presentation will be outlined into these categories, starting with a brief discussion on the waste plastics, how it become a global issue nowadays, and how we can incorporate these composite plastics into asphalt binder, the experimental methodology that has been followed, and the results based on the phase separation and the performance analysis, and followed by conclusions and the future research scope. So if we look into the categories or the generation of plastic, as we all know, the generation of waste plastics has becoming a major environmental issue, and which is also hazardous for the human health. And every year, almost more than 20 million of tons plastics is generating, where the recycling rate is very low, almost 9 or 10%. And if we look at here, we can see in the pie chart that there are different types of waste plastics included. Almost 30% is polyethylene, which is split up to LDP and HDP, and another 30% is covered by polypropylene. And the others are like polystyrene, PVC, or polyethylene terephthalate. Now, as we know that there are different types of plastics, how we can identify these plastics? I mean, how many of you are holding plastic glass or anything in your hand right now? So if you just look into those plastics, there might be somewhere at the bottom or the corner, there is a code for each type of plastic, whether it is PET, LDP, or HDP. So followed by this code, we can identify these plastics. Like for the HDPE, it means high density polyethylene, where LDP means low density polyethylene, and PP means polypropylene, which actually covers most of the 60% of the overall plastic that we saw in our previous picture. So to know better why these plastics is becoming a global issue, we have to know how this plastic recycling chain works. So after the end of their use life, the plastic goes into the trash. We just put them in the dumpsters, and then they sort it out, they move into the recycling industry, and they shred it to the smaller plastics, and then it goes back all the way to the recycling industry for the new manufacturing. Well, this percent is the 10%, what I mentioned in my first presentation, that this is very low as per the overall production each year of the waste plastic. So this 10%, if we can, this 10% only recycled every year. So if we can incorporate these waste plastics into our road infrastructure, then there will be a huge scope to fill up this place with the plastics that goes to landfills every year, which is almost 70% of the overall waste plastics. So now, as we know, the generation of waste plastics has becoming a major issue here. We also know that the pavements in the regions where the extreme weather or due to the temperature fluctuation, we have the frost heaving in the winter, and we have like softening effect or the rotting at the summer. So how we can merge these two problems and find a solution? So we can just come up with that to solve these two problems together. The overall objectives of the project is to formulate a sustainable pavement or HMA mixture design, including the recycled plastics that can enhance the performance to withstand the distresses due to the weather while mitigating the environmental pollution as well. Moving forward, this whole presentation will be divided into three main parts, where the first part is how we can incorporate these waste plastics into asphalt binder. Moving forward, we can see the methods how we can incorporate the plastics into the asphalt binder. Two well-known methods are wet mixing method and dry mixing method. In wet mixing method, where we can see we have to mix these shredded plastics into the hot asphalt binder using a high or low shear mixture, and then we have to put it into the hot aggregates to prepare the HMA mixture. On the other hand, on the dry mixing method, we put the plastics directly into the hot aggregates, and then we put the hot asphalt binder, and then we prepare the asphalt mixture. And here we can see at the dry mixing method how these plastics are coating the aggregates here. As I mentioned already, there are two methods. We have some challenges in these two methods as well. What are these? In wet mixing method, we have a problem which is called the phase separation that I will discuss later in the presentation. And it has a little bit of higher initial cost compared to the dry mixing method due to having some sophisticated equipment like the high shear or low shear mixture. On the other hand, in dry mixing method, we have some serious environmental issue like the microplastics in the air or the potential leaching to the soil. And also, we don't know how much or how effectively these plastics are coating the aggregates. So now, the thing is why we should care about phase separation issue and what is that. So due to the non-compatibility and the density difference between the plastic and the asphalt binder, the plastic after pouring into the asphalt binder, it tends to go up, at the surface of the asphalt binder at the time of storage. So if we can see an animation to better understand this, if we just imagine that this is asphalt binder into a tin, then when we pour the waste plastics, the shredded waste plastics into the asphalt binder, after the time of storage, they usually tends to go up as the density of the plastic is way lower than the asphalt binder. So this problem is called the phase separation issue in the wet mixing method. And what are the problems we face if there is a phase separated plastic modified asphalt binder? So the first, there will be obviously variability in the field construction. It will not be a homogeneous modified binder, so which will eventually reduce the performance of the plastic modified binders, and which will eventually, going to the inconsistent pavement quality, and then we will have premature failure and for the higher maintenance cost. So the solution is, as we have to care about this phase separation issue, if we want to proceed forward with the wet mixing method, the solution is to enhancing the compatibility between the plastics and the asphalt binder by a cross-linking agent to create a homogeneous asphalt binder matrix. With that objective, in our project, we selected two types of plastic. In most of the previous research, researchers use like single source of plastic, like only LDP or HDP or polypropylene. However, in the real field, the plastics are not like that. They come up with a mix most of them are mixed-use plastic. If we just look at the plastic bottle, we can see the top cover of the bottle, which is HDPE, and the lower part is the LDPE. So in real life, most of the time we have the composite plastic, and according to the plastic recyclers, they say that it's sometimes very hard to separate these mixed plastics, and that's why they lose their demand outside for the recycling purpose. So we choose two types of mixed plastic here. One of them is HDPE, which is high density polyethylene, LDPE, low density polyethylene, and polypropylene, PP. So one of them is the mix of these three plastic, and another one is the mix of HDPE plus PP. And after this grinding and sieving, we get into 0.6 mm passing for blending, because for choosing the size and the blending time and everything based on the optimization process, after the whole process, we came up with this size for the blending. And the stabilizers that has been selected is reactive elastomeric tar polymer, which is known as the RET, and another one is polyethylene grafted maleic anhydride, which is PGMA, and sulfur as a cross-linking agent. And this is the experimental methodology that has been followed for the experiments. As we can see, starting with the virgin binder, which is PG5828, considering the extreme cold weather, the whole ideology behind that was if it can be implemented in the extreme weather, then definitely it will be applicable to the standard weather like New Jersey or any other weather where we don't have the extreme weather, but it will be still implemented. So the plastics, both the mixed plastics at a rate of 1, 2, and 3% by the binder weight, and we added the stabilizers. We can see the Elvoli RET 4170 at 1:1 ratio with the plastic, and we also added maleic anhydride at 1% by binder weight. Before going into this mixing or blending procedure, we did the DSC analysis, which is differential and scaling calorimetry, to identify the melting point of these plastics to make sure that they are not getting unmelted where we are proceeding to the asphalt binder, because all these plastics, they has to be melted. So we make sure that their melting point is under the usual mixing or blending temperature, which is 180 degrees Celsius for the asphalt binder while we are mixing with the plastics. And after making sure that we blended with these plastics and each of these stabilizers, and we did the storage stability assessment, which is the problem I mentioned in my previous slides. To do the storage stability assessment, we did separation index, which is cigar tube separation test, and we did the morphology analysis using the fluorescent microscopy. And then the storage stable polymer modified binder that we get, we did the rheological properties and performance characterization as well, using the temperature frequency sweep for high and intermediate PG grading, multiple stress creep recovery for rutting performance, and LAS, linear amplitude sweep for the intermediate cracking resistance, and bending beam rheometer for low temperature PG grading. I will pass through this quickly because this is just the blending procedure that has been followed for maleic anhydride and these two types of plastics. So here high shear has been used for 120 minutes at 180 degrees Celsius for 4,500 RPM. And on the other hand, with the Elvoli, we have a little bit of difference here. We have to use here both high and low shear mixture. Here we can see this is the high shear mixture, and this is the low shear mixture. And here there is different steps on the overall blending procedure, starting with the 4,000 RPM at 180 degrees Celsius. Then we have to shift it back to the low shear mixture at 165 degrees Celsius for another 120 minutes involving the RET. Then, after doing all these blendings and incorporating the waste plastics, we are going to the second part of the presentation, which is the phase separation assessment. For this, we did the cigar tube separation test according to the ASTM D7173. Here, after blended all these plastics modified binder, we poured into an aluminum tube, and then we kept it vertically for almost like 48 hours at 165 degrees Celsius, and then we shifted back to minus 10 degrees Celsius for another 5 hours. And following that, we discarded the middle portion of the tube, and we kept the top and bottom portion of that aluminum tube, and we ran the DSR analysis to get the G star and sine delta. So the G star and sine delta, the ratio of G star and sine delta is called the complex modulus separation index, which is the desirable value should be 1 if the modified asphalt binder is homogeneous. That means the G star and sine delta ratio from the top and the bottom, it should be equal if it's a homogeneous mixture. With the desirable variation with 20%, we can get, from 0.8 to 1.2. If we look at the results that we get from the separation index text, we can see these are the values, the SI or the separation index values for different types of plastics. On the left side, we can see the separation index values for LHP plastic with the stabilizers, and here we can see with the HP plastic with different stabilizers. So if we start with from the very beginning, we can see with very low percentages of plastic, there is not that much difference with the stabilizer with or without. However, when we add 2% of plastic, the separation index goes so high so that we can definitely see that there is a phase separation and the plastics is moving to the top. However, when we add the maleic anhydride and the RET stabilizer, we can see there is an improvement for both LHP and HP plastic in terms of phase separation. That means both the maleic anhydride and RET, they are showing noticeable improvement in storage stability, at least in terms of 2% of plastic. To better investigate this separation index, we did the fluorescence microscopy at the both top and bottom sample to see the polymer distribution and in the blended mixture. So we can see the top portion of the binder and the bottom portion from the tube that we get after the polymer modification. So we did the fluorescence microscopy using a fluorescent microscope, and then we can see the difference here clearly at the top. The white globules, these are the presence of plastic here at the top, and at the bottom we can see there is no plastic. So this is called the phase separation, and we can clearly see it from here. So these are the different fluorescence microscopy images that we get for the storage stable binder that we got from the separation index values. So here we can see for the HP plastic and LHP plastic with 2%, both the stabilizers are performing well. However, if we look deeper, that with the HP plastic, the polymer distribution is not that visible or clear. On the other hand, for LHP plastic with the RET stabilizer, the distribution of the polymer or the plastic is very visible at the both top and bottom. So from here, we can see the LHP2 plastic is performing better with the RET than HP 2% of plastic. Now, going to the last and third phase of this presentation is the laboratory performance evaluation of these storage stable plastic modified binders. Starting with the PG grading, we can clearly see that after adding the plastics for both the LHP and HP plastic at the right side, the high PG grading is definitely improving. However, they are compromising the low PG grading. But apparently, when we add the stabilizers like the maleic anhydride and RET, we can clearly see that these are improving both the high and low PG grade, where LHP2 with RET is maintaining the low PG grade almost similar to the control binder, which is PG5828, and also is improving the high PG grade here. So from here, we can see RET is performing better than maleic anhydride in terms of both HP and LHP plastic for high and low PG grade. To further assess the performance at high temperature, we did the rotting characteristics analysis using the multiple stage creep recovery test, where we get the percentage recovery and the JNR value, which is non-recoverable creep complaints. So the higher the percentage recovery is for a polymer modified binder, the better the performance of that binder in high temperature or in rotting resistance. So from here, we can clearly see with the virgin binder and with the plastics, if we go down with the stabilizers, we can clearly see that the percentage recovery is increasing with the both HP and LHP plastic, where here again, LHP 2% plastic with RET is showing higher results with the RET in percentage recovery. On the other hand, the lower the JNR value is, the better the performance will be in rotting resistance. So here we can again clearly see the LHP with the RET is showing the lower JNR value than the HP or RET combination. From here, we can again say that the RET is exhibited the lower JNR and higher percentage recovery, indicating that it enhancing the rotting resistance across the various stress, as we did the test on 0.1 and 3.2 kilopascal. Now, moving forward, we also did the fatigue life analysis of these plastic modified binders. And here on the left-hand side, we can see the LAS test at 2.5% strain, and the right side we can see at 5% strain for the LAS analysis. And here, starting with the very left corner, we can see after adding the plastics, there is a reduction for the both AHP and LHP plastic comparing to the virgin binder. And however, following the same trend, the maleic anhydride and RET stabilizers is increasing the fatigue life, where we can clearly see that RET is outperforming the maleic anhydride in terms of fatigue life increment. So at 2.5% strain, the HP plastic with RET it performed pretty well. However, with the higher strain at 5% strain, we can see the trend of reducing the fatigue life, but the LHP and RET, it has less reduction in terms of fatigue life with the RET combination. So from here, we can conclude that RET is enhancing the fatigue resistance, which increases the flexibility in the modified binder matrix, thereby promoting the better crack resistance. And we also, for the LS test, we did the frequency sweep and amplitude sweep. This is the amplitude sweep results that we get for this modified binder. From here, we can clearly see on the x-axis effective shear strain, and on the y-axis of effective shear stress, we can see here the light blue line, which is LHP2 and RET2, is showing the higher failure strength with the peak stress, which means it's showing the ductility of this modified binder. So from here, we can again see that the RET modified binders, both for the HP and LHP here, especially for the LHP, is performing better, is showing the ductile behavior, which was helpful in improving the cracking resistance that we have seen already in our previous slide. So what we can conclude from these results? First of all, we identified the homogeneous mixture, or there was no phase separation issue in wet mixing method with this maleic anhydride and RET 4170 stabilizers with the 2% plastics. And between maleic anhydride and RET 4170 showed the noticeable improvement in terms of high and low PG grade, enhanced rotting and fatigue cracking resistance compared to the plastic and maleic anhydride modified binders. And it's worth mentioning that we also did a comparative study with the plastic and RET modified binder with the conventional polymer modified binder that we have in our industry now, which is SBS modified binders. And surprisingly, we found that plastic RET modified binder showed enhanced rotting, higher fatigue life, improved stress relaxation capacity, and thermal cracking resistance compared to the conventional SBS modified binder that we have now. As a recommendation, we can say that the improved storage stability and performance of composite plastic modified binders can be achieved using the stabilizers such as the maleic anhydride and RET up to 2% of plastic, whether it's mixed or single-use plastic. And among these, RET has performed better in comparing to the obviously plastic modified binder and the modified binders with the plastic and maleic anhydride. So what can be the future research scope? As we did the study in the binder level, so to get the real-life implementation of this HMA pavements, we have to conduct the study in the HMA mixture level to see whether the performance we are getting in binder level is transforming to the mixture level as well. And as we compared only the maleic anhydride and RET, where RET is performing better, there are different types of RET out there. So we can compare with the LHP plastic that was performing better here with other types of RET to see if it's following the same trend or is performing better. And last, but the most important thing, we have to look for the long-term performance data and to conduct a life cycle cost analysis for this storage stable modified binder to see their cost efficiency. So how this study can effect or give benefit to the government agencies like NJDOT. First of all, it's going to give the enhanced performance with improved rutting and cracking resistance of the asphalt pavement, and eventually it will give a longer lifespan of the road, and which will reduce the maintenance cost. And most importantly, it will help to fill the sustainability goal of SDG 11, which is the sustainable cities and communities, by incorporating these waste plastics, preventing the environmental pollution and supporting the circular economy, like the plastic recyclers or the contractors or the government agencies like the NJDOT. So these are the references that has been used for this presentation, and thank you all for your time. I know it's been a little bit boring after the lunch, but thank you all for hanging on there. And if you want to know more about our research, our lab, you can just scan the QR code to see what type of research we are doing in our lab. If you have any questions or suggestions, please. A little bit late.
Yeah, no, it's fine. We're a little behind on time. If we could take one question if we have a quick one. Seems we have one here. If you can come up to the microphone, that'd be great.
The price of material if you do this recycling, conventional and non-mixed.
Sorry, I can hear you actually. Yeah, now I can hear you.
Price difference from virgin mix to using this polymer, is there a big difference in price? Because it looks like you got to process.
Yeah, that's a really good question. To proceed with that, actually, that's what I have already mentioned, that to have a benefit cost analysis, we have to do the life cycle cost analysis with these plastics. But for the preliminary study, if we consider the price, it depends on two different things. If we look at the performance, standard performance, then definitely with the virgin binder, it can obviously cost a little bit higher. However, if we consider the waste plastics that the recyclers, they don't want to keep in their storage because of their less storage capacity. So if you want to get rid of those, and in terms of implementing the RET, if it's giving the better performance in the long run, then in benefit cost analysis, it's going to give the better results with the plastic and RET.
My other question is, when you come to the life cycle, can it be milled up and recycled like millings are done?
Yeah, that's another good question. For that, we have to, implement in the real field, and then we have to see. But as per the other researchers have been in literature review, they mentioned that they haven't seen any problem till now in milling or recycling it as a wrap, but that has not been confirmed by anyone that we will not face any problem or not. Thank you so much.
Okay, thank you. All right, thank you. And I did promise one trivia question before the next presentation, so we'll quickly do this one since we are running a little bit behind. The way this is going to work,
Thank you.
if you think you know the answer, raise your hand. You're allowed to use your cell phones. First person to raise their hand, I'll point to you, walk up to the mic, tell me the answer if it's correct. Oh, yeah, we'll take that. If it's correct, then you win a prize. It's a PE study guide. So if someone mentioned maybe taking one of these pumpkins instead, if you want that, I'm sure you could walk away with that too. But so let me start with the first question. What is Newton's third law of motion? What is Newton's third law of motion? Again, you can look it up on your phone, so if you're a fast texter and can raise your hand, by all means. Okay? So Newton's third law of motion.
The Newton's third law of motion is for every action there is an equal and opposite reaction.
That is correct. Okay. And yeah, the written definition, for every acting force between two bodies, there is an equal but opposite reacting force on the same line of action. All right. That being said, let me get this next presentation ready. Okay. So our next presentation will be on evaluating internally cured not the next presentation.
That's the
Oh, this is, okay. All right. Evaluating internally cured high-performance concrete life cycle cost savings in New Jersey bridges. And this will be presented by Professor Osbe, who is a professor at the NYU School of Engineering. Ooh, we got one more fun fact on you here. He is also the founding director of the C2 Smart Center at NYU.
Thank you. So can you hear me? All right. So before I start, let me see if I, okay. So it's hard to believe that this is the 27th Research Showcase. I was here at the first one with Nick Vittila. I don't know if anybody knows Nick Vittila. Nick was the head of the Bureau of Research, and I was a young assistant professor. And at that time, this was kind of a new idea, so it's been 27 years. So when you get older, you have all these stories. So I don't know where Nick is. I asked Professor Nassif, who is the PI of this project from Rutgers side. He said he might be enjoying sun and ocean in Florida. So that's good. So anyways, this is a project that we have a small involvement as NYU. So the project is much bigger. But what Islam presented at the end of his presentation is a good segue what we're going to talk about here in this presentation. Actually, the life cycle cost ideas for a different material. I'm not a material person. That's why I insisted that Hani should stay here. All the questions goes to him. It's excellent research about high performance concrete and the materials that we're going to talk here from the cost perspective. So again, I'm going to go beyond my comfort zone. These are three slides that are given to us by Professor Nassif's group. So basically, this kind of shows the problem that we are dealing with here. So basically, there's a problem of curing. And actually, I'm a good student. Having worked with Hani for more than 25 years, I learned. I'm a intelligent transportation systems, transportation decision-making professor. But I learned a lot about concrete and materials and curing, having worked with Hani. So I know what these slides are saying, basically. So there's a problem of curing when you pour concrete, and there are ways to deal with that. If you don't do the curing well, there'll be cracking. If there's cracking, there'll be problems later on. So there's a result. There's a drive to fix this problem. And then the important part of this, as far as this presentation is concerned, if there's cracking due to how you treat the concrete in the beginning of its life, there'll be a problem during its life cycle. And that will create problems about maintenance and more maintenance, more rehabilitation, and so on. And it will increase the life cycle cost of that bridge deck eventually. So there is it looks like there's a lot of new research that Hani's group is doing at Rutgers and dealing with internal curing. So basically, it's a better way of curing, and this is an explanation of how this is done. So basically, the whole idea is instead of doing some traditional way of curing, you want to use advanced methods like pre-wetted lightweight fines, superabsorbent polymer, and so on that will release water inside the concrete. You keep sustain the internal humidity doing that, and all of that is just to avoid cracking during the curing process. So that's kind of the explanation of why we are doing this method overall. So this is the importance of internal curing. As I said, it allows reduced cracking. It allows later on problems with the bridge deck and then deterioration and then so on. So that's the whole up. Of course, what we want to do is there are more traditional materials like regular concrete, high performance concrete. We want to compare the cost of these methods with this more advanced concrete, the material, and then see if it really makes sense over the lifetime of the structure. And as Islam said, this is important because something that might make sense in the lab or in a small scale has to make sense at a large scale. So that's the whole goal. This is the project objectives, not for our project, but for the whole project. And as you see, the life cycle is the last bullet, looking at the life cycle benefits expected. And let me just go back to Nick Vitulo days. This is actually one of the first projects I did almost 25 years ago when I started as an assistant professor at Rutgers before I moved to NYU. So basically, there was a gentleman called Dick Weed. None of you would know. Dick has been with DOT for a long time, and he was interested in life cycle cost analysis, and he created a project. This is my introduction to life cycle cost analysis because I was doing more technology, intelligent transportation systems. So Dick created a problem statement like you guys do today, and we were able to get that project awarded to Rutgers at that point, I think 1998. So this is, some of you are not even born then. So what happened is Dick was obsessed with one thing about life cycle cost analysis, discount rate and inflation. And at that time, this was not a big problem. And actually, there were a lot of discussions with our other university, another professor from City University of New York. Is that important? Do we really need to care about discount rate, inflation, because we really don't have great problems with that, and so on? But it was our introduction to life cycle cost analysis, and then me and my PhD student, we wrote the first kind of guidelines for life cycle cost analysis for NJDOT. It's still available online. You can find it. It's one of our also papers that we wrote together that was highly cited. So I think that ideas, some of the ideas that we developed at that time, we're still using them here. And actually people are still referring to our paper. That means they're learning from our paper. One side note, life cycle cost analysis is generally used for structures, material projects, but we also apply them to intelligent transportation systems. In that realm, there's a difference because these projects are very long-term projects. So talking about 50 years, 75 years, ITS projects for life cycle is 5 to 10 years maximum. So you need to have different ideas how to use life cycle for that. So having said all of that, so life cycle cost analysis is an engineering economic tool. It's important because it not only considers agency expenditures, but also user cost, so drivers, commuters, and so on, and also what we call external costs, social costs. So this was important, and actually this was one of the key points that we even at that time discussed, because how do you incorporate these different cost categories in your life cycle cost analysis is important. Here we don't, because it's a very small task, we don't go into details of how to incorporate them individually. So, but I'll just give you an idea, and also you can think of it for other projects, what it means to have different cost categories. So in our work, and in general, people just use deterministic life cycle cost analysis. That means they fixed the input, and then they calculate the life cycle cost for a period of time, whatever that period of time is. But what we advocated is, because you're dealing with such a long period of time, it's more appropriate to do a probabilistic life cycle cost analysis, meaning you need to assume that your variables might change probabilistically within certain limits over that lifetime. And then you want to calculate that probabilistic values using something like Monte Carlo analysis, and then your life cycle then will become a distribution of possible life cycle costs, and then that you compare the distributions, basically. The last bullet is CO2 emission analysis. This was, I think, kind of an idea that came about during the project meetings. I'm not sure if it's going to stay in the final report. The final report is not out yet, but I'll show you some of the ideas, results, but it might not be in the final report. But that's also an interesting thing. Okay, so the life cycle, the objective function for LCCA is a large function that's made of different costs. So you have agency cost, you have salvage value, you have time cost, value of time cost, you have crash costs, what you call externalities, and then the emission cost and so on. So the different cost categories. But in general, there's 3 cost categories: agency cost, mainly cash. There is user cost, basically the operating cost and congestion cost. And then there are other externalities like emissions, noise, and so on, due to basically the cycle of repairs and traffic congestion that might be creating this indirect, so-called indirect costs. And then, of course, for each of these, you have to assume some values for the parameters so that you can calculate this function over, let's say, 50 or 75 years. You don't want to do that manually, especially if you assume that you have thousands of bridges. So we have actually part of a different project that we work with Missouri DOT and US DOT. We developed a spreadsheet that you could use to calculate these costs for different types of bridges automatically using whatever the input values you want. So you can actually enter the cost variables. And in this presentation, you will see federal highway recommended values. These are not necessarily what NJDOT uses. And in the final report, we will have the NJDOT numbers that they were made available to us last week after Janet Lady got the presentations, and I didn't want to go back to her and say, tell your IT people, we changed all the numbers and we need a new presentation. So but the NJDOT numbers also will be in the final report. But the spreadsheet is very easy. In fact, when I did the project a couple of times for different occasions, we tried to do a web-based version of this, and it has its own complications. So the best way to do it was to have a regular Excel spreadsheet that anybody can use. So these are the numbers. So I kind of put the caveat, these numbers are not necessarily NJDOT numbers. These are the numbers that we assumed based on federal highway assumptions. Obviously, every state is different. The practices are different, but this gives you an idea. For regular concrete, is like 22 years of service life, HPC 40 years, HPIC 63 years. Again, for NJDOT, these numbers might change. Material costs are the most tricky ones, and I don't have to tell you that they're changing every day. There's a new tariff. It's 100 times more. There is more inflation. There is 50 times more. So these are, again, the material numbers that Professor Nassif's student got from manufacturers, we got from the literature. But again, we also have numbers from NJDOT that we will add here, and they're not the same. They're different, actually. But the good thing about the spreadsheet, if you have the numbers, you put them in, and you get the overall life cycle. Of course, you need to also make some other input assumptions, like average daily traffic, truck percentage, annual growth rate, number of lanes, and so on. There are a couple of things that you have to be careful here when you do this kind of long-term analysis. You cannot grow, for example, the AADT indefinitely. So you need to have some constraints on certain variables that are physically, they should physically make sense, especially if you're looking at one segment, one bridge. So that's also in the spreadsheet. So basically, So what we want to see is if HPIC versus the HPC is more beneficial in terms of service life, agency cost, and overall social cost. And then to do that, we took one bridge from IAD, and then we put the variables related to that bridge into the spreadsheet. And then what we found out that HPIC is much more advantageous with respect to a regular Class A concrete. And also, there's a lot of savings versus HPC. But as you see, these are some numbers, like point estimates that we are using. But at least it gives us an idea that this new method, due to less cracking, less long-term rehabilitation and maintenance needs, it's going to be much more advantageous than other two methods. And you see here, compared to HPC, 15% less agency cost, user cost can be between 10 to 40%, social cost is around 10%, total cost savings between 15 to 25%. So if you multiply that with all the bridges that you will build or rehabilitate in the near future, obviously that might translate into some meaningful numbers. Then but I say, but we want to do a little bit more than that. We want to, because it's a long time period, so we want to take the uncertainty into account, and we want to do a probabilistic associated. Means we're going to withdraw this. We're going to draw these variables values from a distribution, a predetermined distribution, and we will use Monte Carlo simulation to calculate HPC, the life cycle cost analysis for HPC and HPIC many times to see how they change based on these probabilistic numbers that we get from predetermined distributions. And then when we do that 5,000 runs, you can do 10,000, however many runs, and this is not taking too long for a single bridge or multiple bridge. But if you have to do that for 5,000 bridges, obviously it will take much longer time. You can build these distributions for HPC and HPIC costs for different runs. And you see this, they look like a Gaussian distribution. And if I draw the CDFs, then you see that for most of the probabilities, the HPIC remains a better option if I look at the CDFs. So in layman's terms, 95% times of the simulated cases, the HPIC performs better than HPC. So there's few cases where if you're in the tails, some combinations, then HPC might be better, but in majority cases, we see HPIC performing better. Then, if we just, so this was only for one variable, changing the discount rate. But if you change multiple variables, then the simulations become more difficult. So now we're taking discount rates and the service life from a probability distribution. So now you have two probabilistic values, so then you need more Monte Carlo simulations. It might take longer life, and for that one we have the ranges, and then we look at it, then when you have this combination of two probabilistic values, the benefits are not as high as just one variable that we tested, but still they are much higher, better in the HPIC case. So HPIC still outperforms HPC. So finally, so one thing I say, we did this for 8 bridges. If you want to do this for thousands of bridges, you need to do a different way. And if you have to optimize this, for example, for a budget constraint, then you need to do some kind of optimization algorithm that's like a genetic algorithms and so on. They will even be computationally more demanding, but we're not going to do that. We're just basically running this for multiple bridges and then see how this works for different ranges of probabilistic values. So the last one was a kind of a discussion from our projects. So basically looking at the social cost of carbon, and this comes from a paper that was published in Nature So it's a kind of a long thing. I mean, there's no time to talk about that, not our invention, but basically some people looked at the social cost of carbon. That means if some approach releases carbon, it might, in the long run, might have effects on environment, and they kind of quantified this effect. And then we tried to do some very simple analysis based on the values in that paper. And what we found out that the HPIC has, again, higher benefits, even though it has some higher carbon release in the beginning over a long time at different discount rates. Again, I don't know if this is going to stay in the final report, but this was a discussion, and this is some results that shows that even the initial carbon footprint of this method is a little bit higher than the regular HPC. In the long run, due to its advantages, it still becomes superior to HPC. So the conclusion is that for most of the bridges that all the bridges we tested, HPIC costs are lower than the HPC costs. The agency savings are around 30 to 50 for using HPIC versus regular concrete. HPIC versus HPC, that's between 15 to 25%. Again, if you think about the number of bridges, number of projects, that might be some meaningful savings. We also did the probabilistic analysis that showed similar results, maybe lower gains due to the possibilities and combinations of different probabilistic values. In social cost analysis also, HPIC turned out to be more beneficial, although its initial carbon footprint is a little bit higher. So that's pretty much where we are. We are still, the report and results are being reviewed. We are adding New Jersey numbers, and I don't know exactly, Hani knows it better than I do. There'll be a final report that'll be available to NJDOT. So with that, I'm going to stop and see if there are any questions.
All right. Thank you, Professor.
That sounds like my class.
Yes, this is good. Again, we're running a little bit behind, but not too far behind. I'll try to do one more of these trivia questions before we get started on the next presentation. Okay, so I know people have to go to other breakout sessions. Feel free to get up and leave when you need to. On to our second question, and again, even just a general definition of this one will suffice. The question is, what is a load cell? So raise your hand if you think you have the answer. Again, the question is, what is a load cell? And even just a definition as to around what it does is fine. It doesn't have to be too technical. And again, you can use your phone if you want to look it up just to be sure. Load cell. We'll give maybe 30 more seconds for someone to raise their hand, and then I'll have to give it to you guys. Okay, looks like we got somebody.
No one wants to answer it, I'll answer it.
Okay, thank you.
I guess a load cell is a sensor that turns a force into electricity.
That's correct. All right. So, and the full written definition here, it's a transducer that converts a tensile or compressive force into an electrical signal, and the signal can be used to determine the magnitude of the force. So, correct. Thank you. All right. That being said, let's move on to the next presentation here. All right, our next presentation will be on real-time monitoring of far-field cracks in concrete bridge decks using distributed acoustic sensing techniques. Our presentation will be performed by Yao Wang, who is a PhD student in the Department of Civil, Environmental, and Ocean Engineering at Stevens Institute of Technology. So whatever you prefer, if you prefer to speak into here. Okay, here's the clicker.
Oh, okay. Let me try. Hello, everyone. Good afternoon. I'm Yao Wang from Stevens Institute of Technology, and my professor is Professor Yi Bao. Today, I will show you our latest research, real-time monitoring of far-field cracks in concrete bridge decks using distributed acoustic sensing techniques. And my presentation will include 6 parts. First is about the background. In 2025 infrastructure report card that showed America's infrastructure, it got an overall grade C, which is a significant signal to more investment and to a new solutions. If we look specifically to the bridge, the average bridge age is about 47 years, which is nearly to the original design life, 50 years. That means we should do regular crack monitoring and also maintenance. Although there are already some existing crack monitoring techniques, such as acoustic emission, static distributed fiber optic sensing, and also robot-assisted inspection, they all have different advantages, such as far-field crack monitoring and finer spatial resolution, and also reduced the human intervention. However, if we use them in the far field and the long distance infrastructure crack monitoring, especially the bridge, it has some disadvantages, such as expensive. Due to the acoustic emission is a point-based sensor, and they are so expensive if you lay out a lot of sensors. And second, the static DFOS, which is only suitable for near-field monitoring. And as for the robot-assisted inspection, it's only suitable for surface and visible cracks. So that's led us to focus on emerging techniques, which is called distributed acoustic sensing and also called DAS. It's based on relay backscattering, and it is already widely used in the traffic monitoring and seismic monitoring and also marine life monitoring. So it's already shown it has a far-field monitoring, real-time monitoring, long-distance monitoring with cost-effective. Then we have proposed this method. At first, we installed the fiber optic cable at the bottom of the bridge deck. And when the crack initiates or propagates, it will generate elastic waves, which can be captured by our fiber optic cable. And at the real time, you will see the stream at the data acquisition system. And by analyzing the DAS signals, you will find where is the crack. And after we proposed this method, we are thinking about whether we can validate it. So we try the multi-physics finite element analysis. And our model is based on a typical highway bridge in US. And to be conservative, we have used a very extreme small amplitude, which is 1 megapascal amplitude twin burst wave, to simulate the cracking signals. And to validate it, we have used the FHWA report, wave propagation in concrete. And after we proposed the method and after we done the numerical simulation, we are thinking about whether we can transfer the results, the simulation results, to the real DAS signals. Because most researchers have overlooked that. They think the simulation results is just the real results, but actually not. Because the simulation is influenced by the mesh and other dimensions. And also, the DAS system have different configurations, like gauge length, channel spacing, and sampling rate. So we have done a data processing, and we proposed it to use cleaning, moving average, spatial downsampling, and temporal downsampling to achieve the conversion from the simulation results to the DAS signals. And then I would show you our preliminary results. The first question, which is very important, is whether crack can be monitored. And at first, we set a clear criterion that we assume that if the DAS signals we captured exceed DAS sensitivity, which is nanostring, then we can assume that the crack can be monitored by the DAS. And as shown here, with the analysis of our results, we found crack larger than 20 millimeter length and a 20 millimeter depth can be monitored at 6 meters away. And even for the crack with 20 millimeter length and a 10 millimeter depth can be monitored at 3 meters away. And also, we found fiber optic cable layout under the bridge deck are more sensitive to the deep crack, which is really easily to understand because if we have a deeper crack, the propagation path from the crack to the fiber optic cable, which we have a layout at the bottom of the bridge deck, the propagation distance will be shorter and attenuation will be shorter. And then if we got the DAS signals and we don't know whether it belongs to the crack or belongs to the traffic or pedestrian, so we have using a method which analyzes the frequency. And here, also to be conservative, we have used an extreme small frequency for the cracking signals, which is 15.4 kilohertz. And we have set a monitoring point at far field, 6 meters away, and also at the bottom of the bridge deck. And then we capture the wave, and we analyze it, and we found the frequency spectrum showed that the frequency always exceeding 10 kilohertz, even at 6 meters away. This is significantly higher than vehicular traffic and pedestrian activities. And at last, we are thinking about whether crack can be located by using the DAS signals. So we have done a lot of tests, 60 sets data with different crack size and different distance between the crack and fiber optic cable. And we use two methods. The first one is maximum stream method. And we found the results are not promising. So we proposed another method, which is first arrival picking method. This method has already been widely used in acoustic emission and also ultrasonic testing. And we got a promising results. So after the initial validation of our proposed method, we jump into we want to know what influencing factors will influence the potential performance. The first and most important is the system configurations. As you can see from here, we have done a parametric analysis with different configurations of the system. And we found that especially these three parameters, gauge length, channel spacing, and sampling rate, will significantly change the signals you captured and extremely change the signal features, such as amplitude and also the waveform. So we quantify it as the absolute maximum strain and estimated crack location. And finally, we found that coarse gauge length or lower sampling rates and also coarser channel spacing will lead to underestimation of crack severity. And among the configuration parameters of DAS system, channel spacing exhibit the most significant impact on localization performance. So if you use the DAS system to monitoring far-field crack, it's better to use a finer channel spacing. And there are also other kind of factors, such as acoustic source, such as concrete materials and crack types. As I said before, I have used a conservative 1 megapascal amplitude just to avoid other kind of cracks, whether we don't know whether it can be captured, but we use a conservative amplitude so that we can have confirmed it. And the second is the propagation, especially the path. As I said before, that the steel bars embedded at the concrete will influence the propagation of the wave, and finally cause the reflection and cause the scattering of the elastic wave. It will finally influence the DES signals we captured. And the third one is the noise, especially the environmental noise and traffic-induced vibrations. But as also I have mentioned before that we can use the frequency to distinguish it, because typically traffic and other environmental noise is below 100 hertz, which is far from our cracking signals, which is 10 kilohertz. And the last one is the temperature, which is also very important. Here I have shown that in the previous literature that the researchers have found when the temperature changes 1 Celsius degree, the DES signals will change about 0.2 microstring, which is really high compared with the cracking signals. However, it's also easy to deal with it. We can use the temperature compensation, such as we can install another distributed temperature sensor. And due to the temperature change is always a long-term change, at least minutes or hours. But the cracking signals is at milliseconds level. So it's easily to do the compensation. And finally, we have done comparative evaluation. First is the performance. Although there are already some other existing monitoring techniques, such as acoustic emission and static DFOS. Although the acoustic emission have a higher sensitivity, but it's just a point sensor. We cannot use it in long-term or long-distance far-field crack monitoring. And a static DFOS is have the sensitivity of macrostring, which cannot achieve the far-field crack monitoring. However, DES can do. Then we have done an economic analysis to show you what we can do and to show you the cost effective. We assume that we want to do the crack monitoring at a 20 kilometer long and 12 meter wide reinforced concrete sea crossing bridge. And we have used 3 different methods: static DFOS, DES, and AE. However, as you can see here, if we use acoustic emission, we should lay out a lot of sensors to build a sensing array. And we also need a lot of cables and a data acquisition system, and also preamplifier. But the cost will be much higher. And if we use static DFOS, as I said before, it just have a sensitivity of microstring. It cannot achieve the far-field monitoring. So you should install at least 11 fiber optic cables. However, if we use DES, we can just use a single fiber optic cable and a data acquisition system. It's evidently that DES is found to be more cost-effective compared with other techniques. This is due to the capability of DES perform long-distance far-field monitoring using single fiber optic cables and single data acquisition systems. Then we jump into the final part, the conclusion. Our research have confirmed that the DES-based approach was effective in monitoring far-field crack in the preliminary test. And second, we have proposed first arrival picking method to achieve high accuracy crack localization. And third, by doing the parametric analysis, we have found coarse gauge length, lower sampling rate, and coarser channel spacing will influence the underestimation of the maximum string values and crack severity. Among them, channel spacing exhibits significant impact on the localization performance. And at the end, we have done a case study. And we found for large-scale infrastructure crack monitoring, DAS is an efficient and cost-effective solution. And here are the references support our research. And thank you for your attention.
All right, thank you. And yeah, if there's any questions, we do have time for a couple questions if we have any. And all right, thank you so much.
Thank you.
All right, so we're doing pretty good on time here. While we have everybody, we can move along. Oh, wait, we do have a question. Perfect.
Okay.
And you could just speak into the microphone if that's easier.
Do you need to process these signals?
You mean how to process the signals?
Yeah.
Yeah, actually, as I showed before, that we have here is the signals, but we can also transfer it to the data. So we will gather the data.
Okay.
Yeah.
Which one influence more here? Length or spacing or rate? Which one influence the quality of the data?
So what do you mean by the
The quality of the data, right? There are a lot of noise, right? So which one
Yeah.
you think is more accurate? Is there any threshold values for these?
No, for example, the gauge length, channel
Yeah.
spacing, and sampling rate
Yeah.
is system configuration,
Yeah.
which is when you buy a DS system, it's
Okay.
already have a different configurations, but you should to choose before you using.
Mm-hmm.
So it's like inherent, not what you did.
For concrete is different, for steel is different, for wood is different, right?
No, for different system and from different brand, from different company,
Okay, gotcha.
you get a different, yeah.
Different things, okay.
Yeah.
Okay. Thank you. Yeah.
Thank you.
All right, thank you. All right, so we're going to move on to another of our trivia questions. Now, this one is a little trickier. It might sound straightforward, but I'll emphasize a word here just to make sure everybody knows what I'm asking. And again, before I start, there is a prize. You get your PE study guide, one of the books. Just go to the front desk or the check-in area, and they'll give it to you before you leave. So the question is, just give me 3 of the 7 base units in the SI system. So what are 3 out of the 7 base units in the SI system? So again, you could use your phone. I know not everybody was here for the introduction of this, but you're allowed to use your phones if you want to look it up. It's kind of a tricky one off the top of your head. If you use your phone, it's a little bit easier, to be honest. But yeah, just raise your hand if you think you have it, and then I'll point to you. You can come up to the mic. So we'll give you, okay, we got somebody.
How about like meters, liters, and Celsius? No?
Okay, so no, liters is a derivative of one of the base units.
Okay.
Yeah, and that's the key, is the base.
Milliliters?
No, I'll explain. Okay, I think we have another hand up. So say that a little bit louder. Okay, we will take that one. Okay, and I'm going to give you all 7 based off the written definition we have here. So again, things like liters are a derivative of kilogram and the weight. For example, so the 7 would be meter, kilogram, second, ampere, Kelvin, mole, and candela. Those are the 7 base SI units. All right, thank you. And yeah, thank you for attempting and thank you for the answer. Again, that was a difficult one. That one was tricky. So we're going to move on to the next presentation. Give me 1 second here. All right, and our final presentation is going to be, actually, you know what, we have time. Let's give some people a little bit of time to get in here before we start this one in case there's other breakout sessions that haven't ended. So take a little break. We'll start in about maybe 5 to 10 minutes. Thank you. Let's get ready for this final presentation. Our last presentation of the session will be Beyond the Clock, Sustainable Solutions for Returned Ready-Mix Concrete. Unfortunately, Professor Magoob could not be here today to present, so in his place we have Wayne Rollins, who is also with NJIT. Is that correct? Close enough. Okay, well, you could do your own introduction as well once you begin. But thank you for joining us today, and whenever you're ready, please feel free to begin.
All right, good afternoon, everyone. Everyone can hear me? Okay, I'll come a little closer to the mic. Good afternoon, everyone. So my name is Wayne Rollins. I'm actually a former student of Dr. Magoob's. I was very heavily involved in the CIM program when I was there. I graduated back in 21. Brief history about me. I worked in the ready-mix industry for about 15 years before I migrated to the US. I came here, did the CIM program. It was right up my alley, right in my backyard, coming to New Jersey. Been here over 10 years, but guess what? Interesting fact is, I don't work in the ready-mix industry, but I've remained close friends with Dr. Magoob, and he asked me to fit in for him in his last minute. Again, one of the reasons I was heavily involved in this research many years ago. So that's a brief background about me. Now, the thing about ready-mix concrete industry, ready-mix concrete, I should say, it's all around us, right? It's the most common man-made building material that we use just about anywhere we go in this world. It also has one of the most major impact on our environment. And as such, we decided to do a lot of research into it, specifically pertaining to, quote unquote, the 90-minute rule that is governed by ASTM C94, where, for the most part, the old adage is we reject a load of concrete after it hit 90 minutes, right? So what has happened over the years, over many years, is that there was a lot of wastage. Wastage affects the environment. And like I said previously, the ready-mix concrete industry directly and indirectly have a major impact on our environment, from pollution to how do we deal with waste. It's a major waste generator. So by doing this research, how can we extend the life of ready-mix concrete beyond the 90 minutes rule per se? All right. So I'm going to try my best with this presentation. So part of the research is we did 3 mixes. Mix 1, control, 100% Portland cement. Mix 2 and mix 3, utilizing cementitious materials, in this case 40% slag and 25% fly ash. We actually did the research at an actual ready-mix facility so we could emulate realistic results as opposed to doing it in a small mixer in a lab, right? So we chose that option, so we had those sponsors and so on. So we have, this was in Pennsylvania at Sylvie Concrete. We conducted pretty much all the basic tests, from compression tests, well, initial soft wet concrete tests, fresh concrete tests, slump tests, entrainment, temperature, water content, etc. And of course, we made our samples to do compression and flexural tests as well as permeability tests. Because a subsequent set of research that we ended up doing off of this is the effect, the long-term effect on freeze-thaw. Yeah, I think I said it right. All right, so here we have pretty much the targets, maximum aggregate size, 1-inch slump target of 6 inches, air content, and the temperature that we're working with. We also did mixes during the summer and during the fall to sort of get the different results to see what the environment would have, the effect it would have had on the concrete. So here we have pictures of our molds, pictures of tests being done. That's the concrete truck in the back with the actual concrete. So again, we decided to do it on a large scale so that it replicates actual mixing in the field. So, let me see. So one of the things we did, like I said, there were different parameters, different criteria that we used. Summertime, fall, so hot weather, moderate temperature. We also utilize hydration stabilizer and without hydration stabilizer. Also to note is that the only modification we did to the mixes after the initial mix were with the high range water reducer and air entrainment, because naturally as the mix continues, it will tend to lose air, and we wanted to maintain that, that air, 6% I think it was, air entrainment level. What we found is that for the 100% cement, we had to redose about every 30 minutes, and for the cementitious materials with the fly ash and slag, we had to redose about every 90 minutes, right? Of note, no additional water was added. The hydration stabilizer, if we were using hydration and stabilizer, was introduced at the beginning of the mix. And after that, the only time the mix was tempered was with high range water reducer and air entrainment admixture if necessary. So here we have the specimens. So we have a number of graphs. This one speaks of slump. You have mix 1, 2, 3. Remember mix 2 and 3 was with fly ash and slag. And the slump, it didn't vary much except that in the beginning. But as you can see, it pretty much was stable throughout up to 180 minutes. This one represents the air percentage. See, we were able to keep it fairly constant, around 6%. The temperature, if I recall correctly, we started out, freshly mixed concrete started out at about 85 degrees. And of course, as hydration kicked in, it increased by about 10 degrees over the span of that 2 hours, which is not bad considering. Okay, temperature here again. This one is no hydration stabilizer, and as you can see with the hydration stabilizer, I was able to maintain it fairly constant. Compressive strength. So the target compressive strength was 6,000 psi, and we were able to meet the compressive strength even at 180 minutes with those samples. And what we found was that the tests that we did during the fall, the compressive strength was slightly higher than the concrete that we mixed during the summer. And we think that is based on the slower rate of hydration for the concrete. Okay. I'm going to be going through this a little fast. Okay, so we have compressive strengths again. As you can see, the target was 6,000. We were able to meet that. If you look at, well, let's look at the 30-day line on the graph, and you'll see that we were definitely hitting our target beyond the 28 days with the concrete. Same for moderate weather. We hit our 6,000 psi target. So flexural strength is usually about 10-11% of your compressive strength. and we noticed that the flexural strength, there was no significant impact on that either. So as you can see, it's fairly consistent. This one with no hydration stabilizer. With hydration stabilizer, you see it's above 700 psi. Again, fairly consistent. And permeability test, this one was done using the rapid chloride permeability test, which I don't know if any of you are familiar with it. It's basically applying an electrical current across a specimen and reading the conductivity. Okay, as we can see here, results fairly good. All right, so summary of the research is that we found that the mixes, they were workable up to about 150, 180 minutes. The 100% cement up to about 100 minutes, which was just a little bit over the 90 minutes. I think I mentioned earlier that in the hot weather for the 100% cement mix, we had to reduce with high-range water reducer and air entrainment just about every 30 minutes, whereas with the slag and the fly ash, just about once every hour. So the slag and fly ash was able to maintain, especially the slump, was able to maintain its slump and workability much longer. Here we go, slag and fly ash, work up to 180 minutes. During the fall, again with the cooler temperature, all the mixes had extended working times very comfortably. So again, we found that the compressive strengths during the, for the mixes that we did during the fall were higher than the ones that we did during the summer. And we feel that is because, again, the rate of hydration was slower. So, you know, the mixes got, and we have to reduce, we have to retemper the mixes less. Right? We were able to meet our 6,000 psi requirement. The ones with hydration stabilizer basically gave us better results. The flexural strength was good, about 11% of compressive strength. Okay, there was considerable change in permeability. The permeability tests were fairly consistent across all timestamps, 60, 90, 120, 150. So we basically were doing tests every 30 minutes. And of course, without the use of hydration stabilizer, or should I say the use of hydration stabilizer is what enabled us to maintain concrete temperature and slow down the rate of hydration so that we could experience the workability beyond 90 minutes. Right? So hopefully I did justice to that presentation in the absence of Dr. Magoob. Any questions? Sure.
There's a maximum number of revolutions on the drum.
There is maximum. I can't hear you, sorry.
Yeah, if you're able to use the mic, I think it's still on.
What I did gather from you is that you mentioned there's a maximum amount of revolutions on the drum. That is correct.
So if you go 180 minutes, the barrel's going to be turning quite a bit.
That is correct. And that is one of the reasons why we did the research. Because ASTM C94 pretty much governs all of that. From the weight per minute, the maximum amount of revolutions of the drum. You're quite right. But our goal is basically to facilitate the conversation. How are we able to extend the lifetime of fresh concrete beyond 9 minutes so that we could reduce waste become more environmentally friendly, et cetera, et cetera. So our goal is not to vouch for immediate change of the specifications, but to enable the conversation and be able to treat it on a case-by-case basis, because the reality is the technology and mixture technology has improved significantly over the years. And just like how, again, I like to use analogies, if I were to give you your sales guy in concrete, and I give you a flip phone that was made in 1990, you're going to ask me, what am I going to do with this? So we embrace technology when it comes to other aspects. So our goal is encourage the conversation. How can we embrace technology in construction, embrace the technology that with our mixtures, the evolutionary technology of our mixtures, that it can impact positive characteristics to the concrete to achieve those results, right? And I think one of the good things is, a few years ago, ASTM made some accommodation that engineers for a particular project, they can allow such things based on a case-by-case basis. So the goal was not to change the specification, but let's look more closely at it and incorporate what we know, incorporate the knowledge, again, knowing what the capability of our mixtures, how can we use it to reduce waste, to extend the lifespan of concrete, become more environmentally friendly, etc.
And I think we have another spec is that you can only temper the load one time.
There's a lot of specs.
Yeah,
You know,
that's what I'm saying, but all those
concrete-
specs would have to be changed.
Concrete is one of those industries that I think everything has a spec. You know, everything about it has a spec, from the water to the aggregates, you know. But how can we approach concrete on a case-by-case basis? What can we allow, you know, what flexibility can we allow inside it? And times have changed. The time it takes for a ready-mix truck to get to a site now compared to 50 years ago is significantly longer with more traffic on the road. So we have to encourage the conversation. Where can we accommodate changes? Right? Not to the detriment of concrete, not to the detriment of infrastructure, etc. But again, having the knowledge, knowing what admixtures can do, admixtures are amazing. Knowing what admixtures can do for concrete, how can we incorporate it and utilize it to a positive gain? So yeah, there's a lot of specs. You gotta stretch. You gotta stretch a bit. Any other questions? The challenges facing ready-mix concrete today is different, you know, compared to years ago. ASMC 94, the 90 minutes, that has been around for like forever. And again, technology in concrete has grown by leaps and bounds since then. And how can we go with it? How can we implement it and utilize it towards you know, a modern advantage?
All right, Wayne. Oh, thank you so much, Wayne. All right, and that concludes our breakout session for today. Thank you, everyone, for joining us. Take care.